Okay, this is the third video of my spaghetti material properties testing, and we're going to cover a lot of the buckling test, which is very important to spaghetti towers uh, when they're shaken or tested, because most of what's going to happen is a buckling failure of these thin, long pieces of spaghetti, dry spaghetti. So last time we covered area moment of inertia. Briefly, that's um, That's how that's the resistance to bending. Uh, and we learned that besides the material stiffness, the shape of the cross section of a member is really important to the stiffness of it. And that means it's important to the um, buckling capability of it. Something that has a lot of area to it, the area gets bigger. You take the same amount of material that's in a circle and you move it, put a hollow center in it and move it out. That thing, if you think of this circles, think of these shapes extended out from the screen, and then try to imagine bending them. And the bigger they are, the harder they are to bend. And that's the geometric effect of stiffness, which is called the uh, area moment of inertia. And we talked about how to make a piece of spaghetti, how to make the moment of inertia bigger so that it buckles at a higher load. And we're going to talk about the testing now. So this is the likely failure mode. Is it's going to when you push on a piece of long, skinny, long thing, it takes a certain amount of load and then it starts to bend out sideways and then it just snaps, and that's called the buckling strength. And this is the equation for it. There's a derivation of that. Oh, it's right here in this link. I'll put it in the link to the video. Quite interesting, but it takes some knowledge of calculus and stuff. And so I made a test fixture just out of wood where I could put a postal scale, goes up to 70 pounds. And you can put it on here and you zero out the postal scale. I'll talk more about that. And then you just push down on this and try to make this so it's vertical, and then just look at the load on there. It'd be nice to have a postal scale that recorded the highest load and kept it for you, but I just look at it and I kind of when this piece of spaghetti starts to bend sideways, then I just record the uh, the load in grams usually, which is just the weight if you were weighing something. Um, Oh yeah, initial curvature can affect the buckling quite a bit. So you know it's better to build your spaghetti towers and do this testing with the straightest pieces of spaghetti you can find. And to some, there no piece of spaghetti is perfectly straight, and so um, there's a little bit of error there. So this is my testing, and this is different lengths. Okay, 10 inches is how long a piece of spaghetti comes, and so I had a bunch of these things, and I cut them off and tested 9 inches, 8 inches, and so on. And you can see, um, you know, uh, that the buckling load in grams goes up quite a bit when you get shorter. And this is a graph of that, and you can see this is not a linear function. This is the buckling force versus the length. This is length in meters, I guess, and a quarter of a meter 2/10 of a meter. But you can see as you get really short, the buckling load really gets high. And you'd expect that because of what we've talked about the nature of buckling. So, so a 10-inch piece of spaghetti will buckle at a half a pound, not very much at all. But you go down to 2 inches, and all of a sudden that same kind of spaghetti, only 2 inches long, not 10 inches long, can take 11 pounds of force. So it uh, it can get pretty strong if the unsupported length is short, which kind of gives you some ideas about how to make your spaghetti tower stronger. It needs to be supported at shorter intermediate lengths. Now, this is the three types of spaghetti. I had the better goods, which is the thicker tube spaghetti. American and Beauty are pretty similar. They're just thinner. The actual stiffness of the spaghetti, it's all seminola. It's all made of the same, pretty much the same stuff, dry spaghetti. But so this shape has a bigger moment of inertia, and it does quite a bit better than the solid thinner pieces of spaghetti. So you can see here, this is for low lengths down here, and it approaches uh, the compression strength of the spaghetti if you got really short, and that's how you do a compression test. You'd have it really short so it doesn't buckle. But for our purposes in spaghetti towers, we're not going to support it much lower than 2 inches or 3 inches or 4 inches. And so this is a good curve. Here's a video of one buckling test. You just press down and watch the numbers on the scale, and when it just before it buckles, it's pretty easy to uh, to see pretty what it is. There's a little error there, but see right there, 1480, something like that, grams. So, so I tested different lengths of spaghetti, but I also made a little fixtures, kind of interesting, with intermediate supports. We know that the buckling load will go up considerably if we make the effective length shorter, if we support it um, in in different smaller lengths. And we talked about this before. This is 4 times better than holding it in the middle is 4 times better than just doing it full 10 inches. Holding it in two places, divided into thirds, that's a 9 times increase in buckling, uh, critical buckling load capability. Um, so I made this little fixture with little eye hooks, and you can test it, the 10-inch piece of spaghetti with no supports, and then you do it with one support like over here and two supports, so it's divided into three, and then divided three supports divided into four lengths, and four supports divided into five lengths. And so I did the testing with the one piece of spaghetti that way, and this is the results. This is the effective length: 10, 5, 3, 3 1/3, 2 1/2, and 2. And that's the buckling load in grams and then in pounds. And so you can see this is just for one piece of spaghetti. I've gone from a tenth of a pound up to 2.5 pounds just by holding it in these eye hooks. And this would be a great experiment for you to replicate yourselves. None of this is very expensive. A kitchen scale doesn't go up to very high loads. This postal scale cost $30, I think, at Harbor Freight. And the rest of it is just wood and little pieces that I put together. They're scrap pieces of wood and stuff. So it's pretty easy to make. The more supports, the better things are going to be. And we never get near the compression capability of spaghetti here. It's always a buckling failure. So um, this is the three types of spaghetti. I did the same thing with the intermediate supports and came up with some numbers for that prove, yeah, if you can make the effective length of the spaghetti shorter, you're going to get much more load capability. Now, bundle buckling. What happens if you glue a bunch of pieces of spaghetti together and make the moment of inertia different? So, uh, this is the critical buckling load. Pi squared is changes. E is just the material property. You're not really going to change that unless you go to a different kind of spaghetti or a different material altogether. I is the area moment of inertia, and that's when we bundle them together, that's what we change. We make the I bigger. And the length here in this kind of testing is always stays 10 inches. So you can see I bundled the spaghetti together, bonded them together about every 1 inch, and this is the results. So number in the bundle up to 6. The buckling load goes quite a bit higher, of course, more than linear. So this is a nonlinear effect too, which, since we know how to calculate moment of inertia, we knew this was going to, uh, the bundled ones were going to be a lot better. Of course, they weigh more too, but the the increase in moment of inertia and buckling capability outweighs is better than just the weight increase of adding bundles. So uh, this is the chart of that. You can see it goes up pretty good. It's not a straight line. And just by getting six of them, at one of them buckles at 265 grams, and six of them buckle at 6,900 grams, which is way more than six times the 265. So there is a benefit to bundling these, and you might think about that in your spaghetti towers. If I know one particular column or diagonal is going to have a lot of compression load on it, then I should bundle it up and make those double or triple. It's interesting because tripling it makes the area of moment inertia go up more than doubling it. If you can envision the resistance to bending is better when you finally get into a 3 and 4 and 5 and 6. Uh, so this is the three different kinds of spaghetti. Okay, and then this is the last thing I'll show today. I did make a little truss out of three pieces of spaghetti, little pieces of spaghetti in there, just hot glued in. I think I put some strings around here because I know these strings are going to be in tension, and it doesn't matter if it's a piece of spaghetti. So I put just some tiny springs glued to each three of them, and I made two of these, and they weighed 4 grams each, about the same as three pieces of spaghetti, a little bit more because there's a little bit more glue and stuff on here. And they held 700 and 930 grams each, so maybe an average of 800 grams. But if you took three of them together and bundled them, which I did on previous testing, they only held 405 grams. So the idea that I'm making the moment of inertia bigger in the middle of this column is something that ought to be investigated. It looks like it really does provide some benefit here. So the three column truss here held maybe 800 grams. A four bundle, which weighs more than the three bundle truss, just four bundled together sustains 610 grams, and five pieces, which obviously weighs more than three pieces, sustained 800 grams. So just by separating these with little pieces like this and making this kind of a truss structure was better than bundling five pieces of spaghetti. I can do with three pieces of spaghetti, basically what I was bundling and doing five pieces of spaghetti. So that we could do this, a lot of these, and maybe that's what a project would be, is to see what's the how much more benefit is there. Of course, making this kind of a truss takes more time, and which means it costs more than bundling spaghetti together, or even making I-beams maybe. Of course, that takes a lot of work too. So the more complicated it gets, yeah, it got better, got more efficient, um, can carry more load for the same amount of weight, but I did have to build this thing, and so the cost went up, and you'd have to make an assessment of that too. But if I was really going to make a great spaghetti tower, when I see uh, parts of the spaghetti tower members that are in compression, I might consider doing something like this. I will save joint tests for the next video, and just today I'm gonna stop.